This is a video about significant figures. This is an introductory topic. What are significant figures and how do you count the number of significant figures, also called significant digits, if you have a measured value or a calculation?
Not too long ago, the air conditioning unit at my home stopped working. I had to get a replacement. In order to get the right heating and air conditioning unit, I have to know the volume of air that the system is going to have to move. So I need to know how much air is in my house. How much air is in your house? How would you go about figuring that out? Let's see if we can do the calculations. What I needed to do is to calculate the volume of my home. So I need to know the length and the width of the house, which is not so hard to do with a measuring tape. I can find those values. But it was a little more of a problem to find the height. I had to estimate that.
Just to simplify matters, I treated my house as if it is a three-dimensional box. I measured the length as 36 feet 8 inches. I am in the United States, and so I am going to use imperial units here. I measured the width as 34 feet 6 inches. But I did not have a ladder, and so I had to estimate the height. I assumed that since my house has 2 floors, that each floor is about 10 feet, and so I estimated the height as being 20 feet. The volume formula is length times width times height, so I'm going to multiply these three measurements together. There are the numbers with the units. When I multiply feet by feet by feet, I get cubic feet, and my calculator gave me a value of 25,302.3. Now, when I called the air conditioning service, do you think I said, my home has 25,302.3 cubic feet of air? Of course not. I estimated that height. There's no way that I can have an answer that is this precise. So instead, I rounded up and said 30,000 cubic feet. That is what we mean by using significant figure rules. You have to know when and where to round your answer to match the measurements that you use to get that answer. In information technology, computer programming, there's a saying, garbage in equals garbage out. How it applies in this situation is, if you have very poor measurements, you cannot get a very good answer. Your answer is very poor too. Keep that in mind. Your answer to a calculation cannot be better than the measurements used to get that answer. The result of a calculation with measurements cannot be more precise than the measure values used to obtain the answer. The bottom line is, your calculator will give you a lot of digits, but many of those digits are meaningless, and it's up to you to figure out which ones mean something and which ones don't. So you have to apply significant figure rules. So how do you determine which of the numbers on your calculator are good or trustworthy? If you know about significant figures, or significant digits as we sometimes call them, then you understand that what it refers to are digits that contribute to the actual accuracy or precision of a measurement and or the answer to a calculation involving those measurements. So significant figure is any digit that is actually measured plus one last digit that is estimated. Now, if you read a digital screen, such as the small snapshot of a scale that I have here on the screen, that last digit certainly does not look like an estimate, but it actually is. The machine internally has figured out that we should have a 2 there because it's not 1 and it's not 3. So the machine rounded it off to 2. Now, if you have an old-fashioned analog tool, then it's up to you to estimate that last digit. And you really should learn how to do this. Just for example, assume you were taking a temperature with an old-fashioned thermometer and it's calibrated in degrees Celsius. The liquid is between the 87 and the 88 mark, and it looks like it's about halfway between. So I would not report this as 87 or 88. Instead, I actually measured it to be 87, and I estimated it to be halfway between 87 and 88, so I would write 87.5 degrees Celsius. That 5 is an estimated digit, but it is significant. So each of the digits in the measurement that were actually measured are significant, and one more digit, the estimate, is significant. You cannot estimate more than one digit, though. 87.5 is said to have 3 significant figures. Again, you must know significant figure rules if you want to figure out how many digits to round your answer off to, because it is the significant figures that determine how good or trustworthy your answer can be based on how good or trustworthy your measurements were. Here are 2 rulers. Let's pretend like they're measuring centimeters, and there's a little metal object between the 2 rulers. The ruler on the left only has the centimeter marks. I can read that the metal is 1 centimeter long. It is not 2 centimeters long. It looks like it's about halfway in between. So I would read that as 1.5 centimeters. I actually read the 1 right off the instrument, and I estimated one digit, 0.5. If I have a better calibrated measuring instrument, like the one on the right, then I can get more digits in my measurement. On the right, we see the millimeter marks in between the centimeters. We can read those as point something. So the cylinder looks to me to be 1.4 and not quite to the 5. I actually read the 1.4. Those are measured values. I'll estimate one more. I say it's about 7/10 of the way between the 4 and the 5 millimeters. So I will put 1.47 centimeters. Which one of those values would you trust more? The 1.47 has 3 significant figures and is more trustworthy. It's very important that you understand that your calculator is not following significant figure rules. It's up to you to figure out which of those numbers actually displayed on a screen have meaning and which of them are meaningless. It is possible to program calculators with significant figure rules, but most of you will have a factory model set on factory settings, and it will just display every digit it can. Most of those digits are meaningless, and you should not write them down. So how do you know which digits to write down and which ones not to? To determine whether a digit is significant, here are some rules to follow. First, every non-zero digit in a measurement is significant. So anytime you see 1, 2, 3, 4, 5, 6, 7, 8, 9, those count. The problem comes with the zeros. When do they count? When don't they count? Here are three examples: 1.23 meters, 1.23 meters, and 0.123 meters. These all have three non-zero digits. They all have three significant figures. Zeros sometimes are significant, sometimes are not. If the zero is between two non-zero digits, then it is significant. So for example, 103, 103, that zero is significant because the 1 and the 3 are significant. How many significant figures are in these values? (103) has three significant figures, as we just said. I'm going to abbreviate that as SFs. 10.01, those zeros are between two significant digits, so it must be four significant figures. 4.107 similarly has four significant figures. The zero counts. So if zeros in between numbers count, now the question remains, what about zeros that are not between other numbers? If the zero is at the end of a number that has a decimal, it is significant. It counts. We have 33.00. Those two zeros count. 1.30, that zero counts. 4.040, the zero between the fours counts because it's an embedded zero that's between two significant figures. The zero on the end counts because it is a decimal number. So 33.00 has four significant figures. 1.30 has three significant figures. 4.040 has four significant figures. All those zeros count in these particular examples because they're all decimal numbers. That only leaves non-decimal numbers or zeros that instead of being at the end are at the beginning of a value. If the number has a decimal, but there are zeros up front on the left, those are not significant. Those weren't actually measured. They are placeholders to show you where the decimal is, to show you where you are measuring in the number line. For example, 0.005, 0.00045, those zeros on the left are not significant even though these are decimal numbers. Any numbers that have a decimal, the zeros up front on the left do not count. They do not contribute to the accuracy or precision of the measurement or the calculation. If you know how to convert numbers into scientific notation, that 0.005, for example, would change into 5 times 10 to the minus 3 power. Since there are no zeros after the 5, only the 5 was significant. So converting numbers to scientific notation sometimes will help you figure out the significance. If you have a non-decimal number, just a plain old number with no decimal, any zeros on the right are not significant. So for example, if you have 50, 670, 10,000, none of those zeros count. There is one significant figure in 50. There are two, the 6 and 7 in 670. And 10,000 is a big number, but that does not make it significant. Only the 1 has any significance. This is actually a very poor measurement. It seems like there's always an exception to the rule, even this one. All digits written in the coefficient of a scientific notation are significant, as I already noted. If a rightmost zero is measured, or if it is the single estimated digit, then it is significant. So to avoid confusion, you should write it in scientific notation. So for example, if you want to show that you actually measured the 0 in the number 30, it's much better to write that in scientific notation, 3.0, because then there's no confusion. It's clearly got two significant figures. Sometimes people will write 30 with a decimal point. That works. It's just a little confusing because it also looks like a punctuation mark that ends a sentence. There are other situations in which the significance really doesn't apply. We can say it has an unlimited or infinite number of significant figures. For example, if whatever you're counting or measuring can only be a whole number, then it has infinite significance no matter what that number is. If I say there are 30 people here, but only 29 discs, you can only have a whole person, you can only have a whole disc. So since you can only have whole numbers, those have infinite amount of significance. You don't say two significant figures or one, you say infinite. It does not limit how good your calculated answer can be. If the number is a defined quantity, then usually we don't let that affect our significance of our calculation. So for example, if you say there are 60 minutes in an hour, well, that's true no matter how many decimals you use. So it has an unlimited amount of significance to say 60 minutes and 1 hour are equivalent to each other. So just to summarize, all non-zero numbers are significant. The question is what to do with zeros. If they are embedded between non-significant numbers, then the zero becomes significant. Here's a big number, 10,235,000. Those zeros look like nothing to you, but in fact, they must be measured values. And so this has 8 significant figures, a very precise measurement. The example on the bottom is a decimal number. The zeros count there not only because they come after a decimal, but because they are embedded between a 9 and an 8, which are significant. Leading zeros are not significant if there is a decimal or not. Those are not actually measured. They simply are placeholders showing you where the decimal is. Both of these examples have only one significant figure, the 6 or the 5. Trailing zeros are significant if there is a decimal, no matter how many zeros there are. 0.600000000. Those 8 zeros at the end are significant. The 0 in front is not. That's simply written to show you where the decimal is. So this number has 9 significant figures. On the other hand, if you have a 0 with no decimal, then those zeros do not count. 700 million has only one significant figure. It's a huge number. It sounds like a very good measurement, but it's really just an estimate, like maybe the population of a country. So trailing or tail-end zeros are not significant if there is no decimal. Here are some practice problems. Why don't you stop the video for a minute and see if you can tell how many significant figures each of these measured values has. Okay. If we have 12 basketball players, you may have said that that's 2 significant figures, but you can't have a part of a basketball player. So this is an exception to the rule. Since it can only be a whole number, 12 has infinite significance. You do not let it limit your answer. 0.010 square meters. The zeros in front do not count. The 0 at the end does. This has 2 significant figures. 507 thumbtacks. You may have predicted 3 significant figures, but you can't have part of a thumbtack. If it's broken, it does not work and it's no longer a thumbtack. Since it can only be a whole number, this is an exact count no matter What you use that figure in, it will not limit the significance of the answer, so we say it has infinite significant figures. How about D? 0.070020. The 2 zeros in front do not count, but the rest of them do. So this has 5 significant figures. 10,800 meters. The embedded 0 counts, but the trailing zeros do not because there is no decimal. So the 108 are significant. Don't get me wrong, the answer is not 108. It's still 10,800. What we're showing here is that only the first 3 digits, though, were measured or estimated. Those zeros at the end are simply placeholders. 5.00 times 10 to the 6th power. This is written in scientific notation. All the digits in the coefficient of a scientific notation number are significant. So the 500 is 3 significant figures.